Now, you know that there are 360 degrees in a circle. Does anyone know why? It's kind of confusing. Like, it's actually maybe because there's 365 days in the year, but like 365 is kind of awkward. So let's change to 360 to kind of make it like days in the year. I'm not sure. But the 360 degrees and degrees in general is just arbitrary. Someone decided that I'm going to cut up one whole circle into 360 little tiny pieces. Maybe it's because there's 365 days in the year, it seemed like close, but it divides nice into 4. So I can go 90, 180, 270, 360. But 360 is just arbitrary. In fact, if you have a scientific calculator, the graphing calculator has already decided nobody uses this. But on your scientific calculator, if you want to change from degrees, you can change from degrees. We're going to learn what radians are. You can change from degrees to radians. And you can change from radians to gradients. And nobody uses gradients. What gradients is instead of dividing the circle into 360, it sort of tried to be more metric. And instead of a 90-degree angle, they called it a 100-degree angle. Yes, it exists. And there's 400 degrees gradients, 400 gradient degrees in a circle rather than 360. And you can do all the math in gradients. And now all of your angles in your triangle always add up to 200. Ooh, does it bother you a little bit? Maybe. So nobody uses gradients at all. But what became important was, is there a way to measure an angle that's connected to something physical? Because if we connect it to something physical, in this case the circle, then we have a definition that actually means something rather than degrees, which is arbitrary. So what they did is this. What I have in front of you is a perfect right angle triangle. So I'm going to just sort of, there, I made it so it's like this, and like this. That's a perfect right angle triangle. Now if I take this right angle triangle and I push down on this point, can you see that that will bend the other side? If I push down on it just a little bit, I can make it so that this bends perfectly to that side. If I do that, that's the definition of what a radian is. A radian is when the arc length is identical to the radius. Great. Does that help you with your math right now?
No.
Not really. Do you know how to do, like, if I say, okay, I'd like everybody up and point one arm here, and I'd like you to take your other arm and point 1.7 radians. You'd be like, a little bit confused right now, because it's not in your head, right? If I said, do 100 degrees, everybody'd be like, I think I got 100 degrees. But 1.7 radians, I'm not sure if I could do that. So we have to develop some understanding of radians. And one of the ways to help us understand radians is to connect it to the degrees that we already know. We already know that arbitrarily we put 360 degrees all around the circle. My question right now is, how many radians are around the circle? And if 1 radian is equal to 1 radius, right? I could take a piece of string, I could cut the length of my radius, I could measure 1, here's 1, I could measure, there'd be 2, there'd be 3, there'd be 4, there'd be 5, be 6. You're not going to like this definition right now, but we'll keep it really unclear to start with. There are 6 and a bit, this is really technical, radians in a circle. Okay? As far as pre-calculus goes, this bothers us a lot. Pre-calculus is being precise, exact, and 6 and a bit doesn't feel very precise or exact, right? If you're answering questions on your math test for me, yeah, 5-ish. Do you ever answer with ish at the end of your answers in math? Like, what's 2 plus 3? Somewhere between 4-ish and 6-ish, I think. No, we're very exact. We want to know more about this. So we use the ideas that we know. And actually, you already know the answer to this, but you've never probably thought about your circumference formula this way. We have our circumference formula. 2 pi r. You probably have always thought of it that way, but you've probably never thought of it as 2 pi r. You thought of it as 2 pi r, but not 2 pi r. In other words, your circumference formula is a relationship between the radius and the circumference. And the 2 pi, which is, would you agree that 2 times pi is about 6 and a bit? The 2 pi says that one circumference, if you want to count how many radiuses you need approximately 6.28 radiuses to go all the way around your circle. And if you actually draw them out, you won't get your area formula and your circumference formula mixed up again. Because your circumference formula is counting radiuses, right? Have you ever seen your circumference formula written this way? Pi times diameter instead of, because 2 radiuses is really 1 diameter. And this is actually where, oh, I'm going to get off topic, I'm sorry. This is where the discovery or the search for pi began. People realized that no matter how big or how small you make a circle, it doesn't matter how big or how small, if you count diameters, which that would be 1 diameter, would be 2 of those, 2 diameters, 3 diameters, it was always 3 and a bit diameters. Historically, you can even see written things where they said, oh, it's 3 diameters, it's close enough. But mathematicians are kind of like, ooh, no, what is this number? What is it close to? And actually, here I'll draw another circle. Said I was going to get off topic. One of the greatest mathematicians of all time, Archimedes, back in about 300 BC, was like, I want to see if I can get close to this number. And so what he did is he said, well, I am going to draw these perfect, I'm going to divide this nicely into 6 equal sections. That makes these 6 equilateral triangles. And if we use our unit circle of 1, okay, and these are equilateral triangles because these are all nicely 60 degrees. If this is 1, this is 1. So Archimedes was able to say 1, 2, 3, 4, 5, 6. My circumference of this hexagon is 6. Not circumference, my perimeter would be the right, oh, check this out. No, that's a circle. Perimeter is 6. So my circumference has to be bigger. That's pretty sound logic. He's like the greatest mathematician of all time? Yes, trust me. So then what Archimedes did is he said, well, if I take each of these points here on the outside, do them in purple, and I draw tangent lines off of them, it makes a perfect hexagon on the outside. Archimedes was able to measure that hexagon on the outside. Maybe its perimeter, I don't know the exact, 6.5. Let's just, and he's like, ooh, I now know that this special number, 2 pi, hence trying to find pi, because if you wanted to do diameters, you would just divide things by 2. I now know that since my outside perimeter is 6.5 and my inside perimeter is 6, that 2 pi, 6.28, has to be somewhere in between. Okay? And he had the mathematics to figure out all of these lengths and calculate them. He then had the mathematics at the time to say it is not hard to cut any length in half. If I cut that length in half and draw a line, I get a new point here, 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 and here. And if I now connect the points on the outside, instead of a 6-sided shape, I get a 12-sided shape. And I can do the same thing with the tangent lines and make a 12-sided shape on them. And then I can cut that in half and get a 24-agon, and then a 48-agon, and then a 96-agon. Archimedes actually made a 96-sided shape on the inside and a 96-sided shape on the outside, did all the mathematics without a calculator to calculate both of them, and already had pi to 3.14, already had a couple decimal places. And he said, I can get as many decimal places as I want. I could just keep using my method after 96. Right? Even 24. Like if I cut this in half again and join these, this is only 24. This one in half, this one in half. Okay. Oh, I missed. Sorry. That one, and then that one, and then that one, and then that one. This is only 24. My lines are trying to be straight. You see that the red is really, 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 really close to a circle already at 24? People would have said to Archimedes, okay, we had some people that were okay with 3 instead of 3.14 at the time. You've already gone to 96. You are super, super close. In fact, Archimedes sometimes said, well, why don't we use 21 sevenths? I know it's more than 21 sevenths, but why don't we use 21? Actually, I know it's less than 21 sevenths. Why don't we use it as an approximation? 21 sevenths is 3.142857 repeated. It's a little bit more, because if you've memorized pi, it's 3.14. Anyone know the next two? 1.5. Yeah. Okay. So this is a little bit too much, but it's pretty darn close. So the idea of counting how many radiuses around the circle is connected to our circumference, and we can now say that 2 pi radians is equal to 360 degrees. And we can convert back and forth. Halfway around a circle, does it make sense that if all the way around was 2 pi radians, halfway around would be pi radians, and pi radians is 180 degrees. 1 radian from my picture that I drew at the beginning. Okay? So first of all, if you have this picture in your head, I started with an equilateral triangle, 60 degrees. And I squished it so that the edge matched up. So does it make sense that 1 radian is a little bit less than 60 degrees? That visually gives you that a way of estimating. If we want to find it out exactly, I can use, and I find this one really helpful to use for all math going forward. If I know that pi radians is 180, and I want to find out what 1 radian is, what would I have to do to this side? I'd have to divide by pi. If I divide by pi on this side, I'd have to divide by pi on this side. If I go to my calculator and actually see what that is as a decimal, to 3 decimal places, 57.296 degrees. Just a little bit less than 60 degrees. So, you have this information in your textbook. At the top of page 489. This is where we started. The whole thing around the circle is 360 degrees. The whole thing around the circle, how many radians are around the circle? Because every time you have a radian around the circle, you have 1 radian. Every time you have a radius on the edge, you have 1 radian. And your circumference formula tells you that there are 2 pi radiuses around the circle. So there are 2 pi radians in the circle. Hello?
Hi. I'm not interrupting, right?
Okay. So now we have, and maybe you want to put this off to the side. We, in yesterday, and we talked about arc length in degrees as being a proportion of 360 degrees times our circumference. And now we can take that same formula and we can do it in radians. And it would look like this. Instead of 360, we would do 2 pi, because that's how many radians are in a circle, times the circumference. Because 360 degrees is equal to 2 pi radians. And this is on your formula sheet. And unfortunately, this is an example of mathematicians just could not help themselves. I really like it unsimplified, because it's still that idea of proportion of the whole thing. But this is just way too tempting that you can cancel so much stuff out. On your formula sheet, it's been simplified because it just becomes theta times your radius. If I know my angle is 2 radians and my radius is 7, then I know the arc length is 14. It's that simple. So this formula right here, the arc length one, in radians is on your formula sheet. But it only works if theta is in radians. If theta is in degrees, you either have to switch it to radians to use this formula, or you have to use your degree formula, which is not on your formula sheet. All right, so let's go to example 1. And we start by just practicing switching between radians and degrees. So sometimes you're given degrees and need to switch to radians. Sometimes you're given radians and need to switch to degrees. We're going to learn sort of a basic technique for doing that. And then we're also going to learn a couple shortcuts that happen in certain situations. So first of all, the basic technique. The basic technique starts off with the fact that you know 180 degrees is equal to pi radians. From this, you could either figure out what 1 degree is, or you could figure out what 1 radian is. If I wanted to find 1 radian, you see that you'd have to divide both sides. 1 radian, I'd have to divide both sides by pi. So 1 radian is 180 degrees over pi. If I want to find 1 degree, I would have to divide both sides by 180. So 1 degree is pi over 180 radians. These formulas are really similar. So they can be, if you're just straight out memorizing them, super easy to mix up. Again, you can always think of them this way by going, hey, I start off with 180 degrees equals pi. I can develop both of them. Now, if you're changing from degrees to radians, you're going to multiply by pi over 180. Radians to degrees, you're going to multiply by 180 over pi. A way that you can remember this easily. Okay? So in part A, I have 170 degrees. I want to change it to radians. Do I multiply by 180 over pi or pi over 180? Okay? The way that I always think about changing units is if you want the degrees unit to go away, it needs to cancel out. So you need to have degrees on the bottom, and so you'll have to multiply by pi over 180. And when I do this, and you do not have to, like, you could leave your answer like this. You could reduce it to 17 over 18, but you don't need to reduce it. That is perfectly fine. That is an exact answer. If they, like this one, they say, can you approximate it to the nearest hundredth? Then you'd have to go to your calculator. Then you'd have to go to your calculator and type it in. But the 170 pi over 180 is actually better. So that's your exact measurement. And this is an approximation. Part B then says we're given negative 12 pi over 11. They want us to sketch it and determine it in degrees.
Do you have extra copies of quiz 2?
Yeah, I do.
There's a
All right, so in part B, it asks us to sketch, but right now your brain probably can't think of, there's a 12 pi over 11 in radians, can't visualize that very good. So maybe what we're going to do is we're going to do part II first, where we determine what it is in radians, from radians to degrees. So negative 12 pi over 11. Now this is in radians. If I want to get rid of radians and change it to degrees, I'm going to multiply by 180 degrees over pi, because technically the units here of radians and radians, we want to cancel out. So I find that's an easy way to remember. Should I multiply by pi over 180 or 180 over pi? Because not only will your radians cancel out, your pi's will simplify as well. And then I just have 12 times 180 divided by 11. So you could, if you wanted to leave it as exact, you could leave it as this fraction. If you wanted an actual answer, which makes you visualize it better, to 3 decimal places, 196.363. Did it say to the nearest hundredth in our question? The nearest tenth. It is good practice to answer all of your questions to 3 decimal places, because on the exam that's the expectation if it doesn't say, and then reread your question after to see, I've got the 3 decimal places, what did they actually want? Oh, they only wanted to the nearest tenth. So I have 196.4 degrees. There's a negative sign here. I'm double checking my work, so I should make sure that I go through and add the negative sign there. In standard position, if you were asked to draw negative 196 degrees, can you see that you would go in this direction? This would be 180. You'd probably go another 16 degrees. That would be negative 12 pi over 11. But what we want to develop for our brains is to also be able to start thinking in radians and thinking in fractions. So I'm going to show you how to think in radians. Thinking in radians, you know that this is 0 degrees and 0 radians. All the way around is 360 degrees or 2 pi radians. Halfway around is pi. And we start thinking in terms of fractions of pi. Can you see that negative 12 over 11 pi, negative 12 pi over 11, as a mixed fraction would be negative 1 and 1/11 pi. The negative 1 pi would get you there. And now you have to imagine this half of the circle divided into 11 different chunks and go 1/11th more. That's how we think in radians. We think in fractions of pi. Now, a shortcut is possible in this one, and the shortcut you're going to learn is if you get a radian measure and it has pi, and this is a shortcut only if it has a pi. Do you notice that your pi's canceled out and you're left with a 180? So a shortcut that you're going to find when changing this to degrees is that you just replace the pi with 180. That's a shortcut. Because pi radians is equal to 180 degrees, we can do that and it will convert everything as a shortcut. You can still multiply by 180 over pi, it does exactly the same thing, but both give us the same answer. That shortcut only works if you have a pi. So in part C, we don't have a pi. We have 7.5 radians. And I want to change it to 2 degrees. So I would multiply by, and again, if you're thinking, what should I do, 180 over pi or pi over 180? I want the radians to cancel, so I need the radians on the bottom. That's telling me it's 180 over pi. Technically, what's in the green? Just understanding conversions, because you have to convert. In real life, there's lots of things you have to convert, right? We have centimeters to meters, meters to kilometers, we convert things like that. Sometimes we convert between units. You have to convert centimeters to inches. You have to convert Canadian dollars to US dollars if we ever travel to the US again, right? So if your currency is changing, you have to do a change. What's in the green is equal to 1. When you're multiplying by this, you're not changing the answer, you're just changing the units. Because 180 degrees is exactly the same as pi radians. That green circle is equal to 1. And what a conversion does is it says, I give you something equal, I just change the units. So I go to my calculator here, 7.5 times 180 divided by pi. 429.7. I already remember they said to the nearest 10. 400. So circle questions 4, 5, and 7. And we're going to just do a little bit of thinking, some mental math, changing radians to degrees. Okay? So, first of all, a really helpful thing is to think of your circle with 300, I'll put degrees underneath. Since you know 360 degrees is 2 pi radians, and you know that 180 degrees is pi radians, we can do some other ones pretty quickly. Can you tell me what 90 degrees would be in radians?
1/2 pi.
1/2 of pi. So we would write either 1/2 of pi, or sometimes it's written pi divided by 2. Half of pi. See how we just took our ratios and figured those things out? Okay? I am going to give you some where you have to use the shortcut. I'm going to give you radians, and you're going to tell me degrees. Pi over 18 radians is 10 degrees. What's the shortcut? You replace the pi with 180. 180 divided by 18 is 10 degrees. Okay? In grade 12 pre-calculus, the E5 error is if you forget units. The units for degrees is this little tiny circle. You've seen that before? This is the craziest thing that is for units. Radians is the only thing I know of in math that has units where the units are you don't write anything. It's weird. So you do not have to write rads or radians. If you leave it with nothing written, it means radians. And so one of the things you probably did in your homework in grade 11 is you were probably working in degrees and you just wanted to write 180 degrees and you wrote it like this. Just to point out how grave an error that is. When you write an angle like this, it means 180 radians. By not writing that degree sign, mathematically you've written 180 radians. Right? I can jump and do a 180. Pretty impressive, I know. Okay? I did a 180 degrees. 180 radians would be jumping up in the air. I guess if I divide it by 2 pi, because once around a circle is 2 pi. That's like jumping up and flipping over 28 times in the air. So sometimes when we say, oh, I just did a 180, it's like, was that in degrees or radians? It's a huge difference. Now everybody knows you're talking in degrees because nobody talks in real life in radians that way, right? Snowboarding at the Olympics would be terribly confusing if they decided, you know what, we'd like to teach the world more about radians, so we're going to change our commentary and say everything in radians from now on. Okay, I'm going to give you one in degrees. Can you tell me what this would be in radians? 60 degrees. pi over. Sometimes you can use the shortcut backwards. Can you see that 180 divided by 3 is 60? So I can make it pi over 3. It is not wrong. 60 pi over 180. Because you want to change from degrees to radians, you're going to multiply by that pi over 180. So you could write it as 60 pi over 180 and not lose any marks. But it's going to show up lots as pi over 3. So we need to be able to switch back and forth between radians and degrees. Okay? One of the things that sometimes causes confusion, and I just want to point it out right now, okay, is that because we always talk about pi radians being 180 degrees, sometimes people don't forget that pi is still the number 3.14. So you have to remember that pi radians doesn't mean 1 radian. It still means 3.14 radians. But you deal in pi so much that you start to think of this pi as 1. It's a little bit dangerous. So pi radians is still 3.14. That's where we'll end for today.